No. Okay, so what about the arc length if we've got parametric curves? Well, it turns out it's relatively nice. Yeah, again, if we've got y equals f of x, then our arc length from a to b is the integral a to b, the square root of 1 plus f prime of x squared dx. We developed that and saw why that is, but that's for the Cartesian equation. All right, well, if we have parametric, x equals f of t, y equals g of t. What about arc length there? Well, if we go back to this and use a little bit of Leibniz notation, you know, this is dy over dx, and so well, first of all, you know, that's for x is a between a and b. Well, if we're going parametric, we're going to go t from t1 to t2, or alpha to beta, I think they sometimes use, but yeah. So we do that. We are going to go parameter t here for that. Now, our derivative, well, that's in parametric. How do we do the derivative? Well, we do dy over dt over dx over dt and square that. And that's not how it'll actually wind up being. It turns out it's a lot nicer than that may look. And then the dx, well, if we make the replacement there for the dx, same thing as before, dx would be, you know, the derivative of that times dt, or let's just write it x prime t dt, dx dx over dt dt. Okay, that's what we mean by that. So it's dx over dt dt. I guess we could do it that way, but there's something really nice happens. I'm going to plug in this dx over dt, try to move it in here, but to do that, I have to, this is under a square root, so if I want to put that in there, that has to be under a square root. So it's really, and let's do this too. Go ahead and, you know, that means dy over dt squared over dx over dt. We can do that. But this, wouldn't this also be this? Isn't that the same? And then if I distribute that in, here's where it works out really, really nicely. So they're both in a square root now, so I can combine those. So this times 1 is dx over dt squared. What happens when I multiply? So that's times that. What happens when I multiply this times that? Those two are going to cancel out, aren't they? It's just going to be dy over dt squared. That is arc length parametric curves for parametric curves. It works out nice. So you just have to, well, it's a square root, but you do the dx over dt and you square it and add dy over dt to square that. Of course, that can get complicated, as the other we know can, but they're usually nice and give us some that we can do relatively easy. This one works out so very nice. But all right, so let's find the length of x equals cosine qt, y equals sine qt, and t is going from 0 to pi over 2. So yeah, we've got parametric, so we're going to use our little formula shown right there. So t1, t2, so it's 0 to pi over 2. dx over dt, so I need the derivative. So dx over dt, so I use the same notation like we got there. Use x prime if you want, but what is, so how do we do that derivative? Well, I'd probably, let's, don't do it there. Let's do it here. Right? That's what that means. It's cosine t cubed. So dx over dt is, by chain rule, 3 cosine t squared times the derivative of the inside, negative sine t. And then the same sort of thing for dy dt. That's 3 sine of t squared times the derivative of the inside, cosine t. So that's what our derivatives are. It's 3. Let's just say cosine squared t, sine, negative sine of t. But it's not only dx over dt, it's dx over dt squared. So you got to square that. Plus that derivative squared, so it'd be 3 sine squared t cosine t squared, which may look bad now, but actually turns out pretty good. Is that okay? All right, so that's 0 to pi over 2. Square root, that'll be 9 cosine to the 4th t sine squared t plus 9 sine to the 4th t cosine squared t, where it scribbles out. Yes? Well, those have some things in common. So let's factor off a common term. You got 9, it's common. Both of them have cosine squared. Both of them have sine squared. So let's factor off both of them, a 9 cosine squared, sine squared. So if I factor off 9 cosine squared, sine squared off of that, what's left? Cosine squared. And if I factor off 9 cosine squared, sine squared off of that, what's left? Sine squared? But what's cosine squared plus sine squared? That equals 1. So essentially here I've got square root of 9 cosine squared sine squared. What's the square root of 9 cosine squared sine squared? 3 cosine t sine t. Right? So, looked like it was bad, but it was really nice. Okay. Now what? U substitution. U equals sine t, so du is cosine t dt. Get rid of that times dt. So we've got, that's just 3, no. So I did that, that's u, and so du is cosine t, u over cosine t, so that, it's just 3u to u. So you got 3 times 1/2 u squared, and the u, so it's 3 halves. The u is, I call it sine. And now we're back to 0 pi over 2. Right? So 3/2 times sine of pi over 2 squared minus 3/2 sine of 0 squared. That's 0. Sine pi over 2? 1. Okay?